The next speaker is Professor John Abraham. He will talk on IC engines and sprays. To give a brief introduction, Dr. John Abraham is a professor in Purdue University. He obtained his BTech from IIT Kharagpur, MA and PhD from Princeton University. His research interests are multi-phase flows, combustion and its modeling, and computational fluid dynamics. May I request Professor John Abraham to deliver his presentation?
Thank you. I have got this one. Yeah.
This moves the slides back and forth.
Oh, okay. Let me use this one. Okay. So, good morning. The title of my talk is IC engines and sprays. So, this is a very broad topic, obviously, IC engines and sprays. So I was trying to determine what would be the best way to present it. And what I decided to do was the following. There has been a lot of work done in the area of engine sprays, a lot of work done on atomization, a lot of work done on different elements of the spray. And all that is very good. But then I sit back and ask myself the question, if I were to do atomization research, which area of engines would there be the maximum impact? Okay? It is always good to get very fundamental insight into all the problems we are interested in, and understanding things fundamentally gives us a satisfaction, right? I mean, but it's not always clear that that understanding is necessarily going to benefit something that's practical. So the question then I ask is, well, if I have all this research done, where is the most practical impact likely to be? Okay, so keep that in mind as I go through. So that question was in my mind as I formulated the presentation. So it's going to change the tone a bit from what we have probably just heard. So when we design engines, the primary considerations obviously are to improve efficiency, reduce emissions of toxic pollutants, and of course maintain or improve performance and reliability. This we know. Now, if I look at the range of engines that we are interested in, that we employ for different applications, we can broadly classify them, of course, into spark ignition and compression ignition engines. And if I then look at the injectors and injection systems in these engines, I can classify them into low pressure, mid pressure, and high pressure. So what I call as the low pressure would be, for example, port fuel injection, also multi-point fuel injection. They are the same thing. This is referring to a single cylinder. This is multiple cylinders. So this is typically what we have in our automotive car engines that we drive around. Okay, low pressure. Mid pressure, direct injection spark ignition engines. I will give you some pressure ranges in a few minutes as I go along. But mid pressure would be as those employed in direct injection spark ignition engines. They are not very common, but becoming perhaps more common in some operating regimes of automotive applications. And early injection compression ignition engines. Then there is high pressure compression ignition engines, and of course diesel engines. Conventional diesel engines fall into this category. So actually I'll skip this picture, and I drew that picture, a sketch by hand, and then I said here is a better picture which I found in a Bosch fuel injection manual. So what you have here is the engine chamber, and you can recognize the cylinder, the piston, and so on, the exhaust valve, the intake valve. This is essentially a port fuel injection engine system schematic. There are a lot of details here which we won't spend time on. But in this engine, essentially you have an injector that is located upstream of the intake valve. Okay? And this injector is injecting fuel essentially into this port and to the back of this valve. The injection typically lasts during, it typically occurs when the valve is closed. Okay, so it is not as if it's spraying and the spray is actually it's spraying into the chamber. You spray typically when this is closed, and you wet the surface. Then the valve opens, airstream comes in, and so the processes. What happens then is, so when you inject, there is atomization occurring. There is probably secondary atomization occurring. But essentially, it wets these walls and wets the back of the valve. And when the valve opens and you have this airflow, probably there are different mechanisms that take place. One obviously is that it tends to vaporize if the engine is warm enough. If it's not warm enough, then it can actually strip, or even if it is warm, this airflow can actually strip droplets, and so you will have a mixture of vapor as well as drops that come into the chamber. Okay. That's how the port fuel injection works. Typical injection pressures, so these are low pressure, 2 to 3 bar. If you measure the mean diameter of these of sprays from these kinds of injectors, they are typically been reported to be 100 to 200 micron. And as I said, injection occurs when valve is closed. There might be just some residual air motion in the intake port at that time. The temperatures are typically 325 to 350 Kelvin, unless, of course, it's just the cold start period for the first couple of minutes. And the pressure in the port is, of course, atmospheric or lower in non-turbocharged engines. Okay. The reason why you would employ port fuel injection is it allows you to give more accurate fuel metering. Because the injector is located closer to the engine as opposed to a carbureted engine where the fuel was introduced much upstream, there is faster response. You have improved volumetric efficiency because of the cooling in the intake port, and less vapor which actually displaces the air. Less cylinder to cylinder variation because each cylinder has its own port injection, and easier to adapt to alternative fuels. Okay. Now, note that in the case of the port fuel injection, studying the atomization process of port fuel injectors is interesting, but not probably very useful. Those engines function well, but it's not a very useful effort. Okay. Now, a presentation like this obviously has my opinions mixed with the presentation, and I will express those opinions. So now let me move to the mid-pressure range, which is a direct injection spark ignition engine, and this is again taken from a Bosch manual. And as opposed to the previous case, so in the previous case we have the intake valve, and the intake valve is the fuel injector is located upstream of the intake valve. In the case of the direct injection engine, whenever you hear the term direct injection, it's injecting directly into the cylinder. You have an injector which injects directly into the cylinder. Okay, that's just this part here. You can ignore the rest of it. And there are different ways of doing this. You can have an injector which is located here, which essentially sprays, and then the piston might have a contoured surface which allows the spray to turn around, and it then encounters the spark plug, which ignites the mixture, and it is burnt. This can also be, so this is essentially, so this spray is essentially guided to its position by the wall. You can also have the spray guided to its position by air motion within the cylinder, for example, swirl. So then you would call it as an air-guided system. And you can have a spray-guided system where you can have an injector with, say, multiple holes, just as an example, and one of it might be directed right to the spark plug. Okay. Now, in these engines, injection pressures typically range from 10 to 200 bar, and the range is fairly large only because the timing of injection changes depending on the mode of operation. The sort of mean diameter have been reported to be 20 to 50 micron for these injectors, and injection can occur either when the piston is in its intake stroke or during compression. So if you are running the engine in the low to mid load range, injection typically occurs later in the compression stroke. This creates a stratified mixture, and the engine typically runs unthrottled in this case, so it can give you diesel-like efficiency. I mean, that would be the objective. If you're running at a high loads, injection is early, creating a homogeneous mixture. Okay, so there's a range of operation that you can go through depending upon whether you want to run light load or high loads. The temperatures in the chamber during injection are typically 325 to 350 Kelvin. And again, the pressure can be atmospheric or lower in non-turbocharged engines. Just advantages and disadvantages: reduced pumping losses at light loads, higher compression ratios, overall lean burn at lighter load because you are essentially having a stratified mixture. Reduce heat loss at lighter loads because you do not have the combustion taking place close to the walls. But the negative is that because the mixture is stratified, you have richer regions, you can create increased hydrocarbon and carbon monoxide emissions. In fact, even if you have very lean regions, that can also produce unburned hydrocarbons and carbon monoxide emissions. So whenever you have stratified mixtures, this problem arises. And of course, because the mixture is stratified, you can actually form soot. Particulate emissions become a problem as well. Okay, so it's emissions that sort of restricts more widespread adaptation of DISI concepts. Okay, compression ignition engines. So when you think of compression ignition engines, you think of diesel engines as an immediate example. But I have, but really there are a range of modes of operation, right? So conventional high pressure injection, as in diesel engines, but you can also have low pressure injection for low temperature combustion engines, and an example of this is a homogeneous charge compression ignition engines, on which a lot of research is being done. Originally, when this was proposed, the injection actually used to occur in the intake port, just like in a port fuel injected engine, and then it used to mix homogeneously. Okay, so the idea behind the homogeneous charge compression ignition engine is that if you look at a conventional diesel engine, you have a stratified mixture where you have rich regions, and then you have a stoichiometric region, and then lean regions. The rich regions, so it is unlikely to form particulate matter, and because the temperature is low, unlikely to form nitric oxide. Okay, but note that low temperature combustion of the type I'm talking there can be achieved in conventional high pressure injection engines by using extreme levels of exhaust gas recirculation too. Okay, that's another way to do that. Now, low temperature combustion concepts, port injection and compression ignition. The problem with injecting it into the port to create a homogeneous mixture and then compression ignition to ignite the fuel is that it's very difficult to control, right? I mean, so you don't know, depending upon what load you are, depending on transient operation, you don't know, you don't have control over where exactly ignition will occur. And if ignition occurs too early or too late, it leads to loss in power. if you have direct injection of the fuel into the cylinder and then compression ignition, control strategies are easier to develop. Okay. So here is a paper. This is something I extracted from a paper by Huang et al. At Sandia. And they have worked with this early injection, low temperature combustion concept, where essentially the fuel is injected early during the compression stroke. In fact, it could be injected even during the intake stroke, either using a hollow cone injector or just a 8-hole gasoline direct injector. And the idea here is, if you have a homogeneous charge, it's difficult to control it. But if you, so if you inject the fuel into the port, or if you inject the fuel early during the intake stroke, it becomes homogeneous. You can't then control when it is going to ignite. Okay? So what do? You can actually inject the fuel during the compression stroke or later during the intake stroke, which creates a stratified fuel. And that then becomes easier to control because all the fuel will not burn simultaneously. Okay? So that's the essential idea. At light loads, it also can be used to control the carbon monoxide and unburned hydrocarbon emissions. So what happens in the fuel distribution in the engine is, if you inject it, for example, 40 crank angle degrees after the intake stroke begins, this is essentially Pliff measurements of fuel distribution in the chamber at top dead center for different injection timings. So if you inject the fuel 40 crank angle degrees after the intake stroke begins, then by the time you reach top dead center, when combustion typically occurs, it is fairly homogeneous, right? You don't see much stratification. On the other hand, if you inject it much later, say this is 315 crank angle degrees after intake port opens, which would translate to about 65, no, that would be about 45 crank angle degrees before top dead center, then you have high levels of stratification. So this stratification can be used to control the ignition process and the rate of pressure rise, and also control carbon monoxide and unburned hydrocarbon emissions. But as you change it from this condition to this condition, the injection pressures will change, and the atomization of the fuel will change, and so on. Okay? And these are just some histograms also from the same paper, essentially to show that if you inject the fuel very early, then this is actually equivalence ratio. So how much of fuel is within a certain equivalence ratio band? That's really the question. That's really what this curve is, this figure is addressing. And if you inject it very early, then most of the fuel is homogeneous, and so it lies within this narrow band. If you inject it later, closer to top dead center, then it's a broader band, indicating there are richer mixtures, leaner mixtures as well. Okay, so now let's come to the diesel engine. So diesel engine, okay, so the conventional arrangement would be you have a diesel injector, you have multiple sprays from a nozzle. It could be from 5 to 8, whatever. And you have a piston contoured in such a way to match with the shape of the spray. And so this is actually a picture which probably has been reproduced more than any other picture in the world. But it shows you a combusting diesel jet. It was appeared in a paper by John Deck, again from Sandia. And what you see here is the structure of the jet. There are some features which are worth noting, that in this jet, this length here essentially indicates the length to which the liquid penetrates. So beyond that, there is no liquid. Okay? And if you take this to be about 10, 11 centimeters, which would be sort of the half the bore, well, less than the bore, but distance from the injector to the wall, for example. Okay? So this would typically be, depending on the size of the hole and other factors, maybe a centimeter to 2 centimeters. That's all it is. Okay? And the rest of it is, so this is the liquid phase. And liquid phase means that's where you will see drops. Okay? A drop, so continuous liquid, we don't quite know exactly, but that's the liquid phase. And the rest of it is vapor and it's burning. That's the region which is burning at high temperature, and that's the region where cooler reactions are taking place, which lead to the formation of soot precursors and ultimately to soot as well. Now, this is another picture I've taken from the paper of Idicheria and Pickett, also at Sandia. And in fact, much of this information from Sandia can be found at this ECN website that Pickett has put up. And what you see here is this is a inject spray, and what they have done is they have me-scattering images of the liquid phase, and then this is Rayleigh measurements of the vapor phase. Again, the point is being made here that if you look at the liquid phase, it tends to be fairly short. Note that this is actually in millimeters. Okay, so this length is about actually less than a centimeter for this particular injector, and then everything beyond that is essentially vapor. Now, not only that, I don't have results here. It has been shown through detailed experiments done at Sandia in the late 90s that this liquid length is not so much, that liquid length is controlled by the rate at which you entrain the hot air. So if you can actually entrain the hot air faster, that liquid length will become shorter. Okay? This is important because we spend a lot of time thinking about what the drop size should be. The drop sizes are so small that it doesn't make a difference. Okay? It is controlled by how fast you can actually entrain the air. If you entrain it faster somehow, you can make it shorter. Okay? Now, I have to talk about modeling a bit. So CFD modeling is increasingly employed to design and optimize engines. That doesn't read correctly, does it? Okay. Now, models for sprays is an important component of CFD models. Atomization, primary and secondary, are of course important elements of these. Another important component of this is wall interactions, because whether in engines there will always be interaction of the jet with the wall. It's not necessarily the liquid, but of the jet with the wall. And drops are likely to interact among themselves. And of course, it's initially you're injecting liquid, so you have to transfer heat, mass, and momentum. So from the gas to the liquid and so on. Okay, so all these are important things to model. In the case of high pressure injection, as in diesel engines, it is my contention that there is no, it is interesting to know, it is useful to know, it is exciting to know how atomization takes place. I don't think we know, but it is not going to make a very useful contribution to engine design, because if you remember what I said before, the length of that liquid is fairly short. And that length is not controlled by what your drop sizes are as a result of atomization, but really by how much or how fast you can entrain the hot air to vaporize whatever drops are formed. In fact, you can actually, this is from a paper that Pickett and I have in Atomization and Sprays in 2010. And so he had actually measured, in fact, this is the same spray which I showed earlier, Idicheria and Pickett, where they had measured the liquid length as well as the spray characteristics, and also quantitatively measured the distribution of vapor fuel in the jet. And what we have found is that we can actually reproduce all the features of that diesel spray either by using a spray model. this is essentially a virtual liquid source. I won't get into that. Or else a vapor jet model. In fact, you can assume that you're just injecting vapor jet with the same mass and momentum as the liquid, and you will be able to reproduce it just as well. Okay. So there are some, these are some actual calculations that we did. This shows mixture fraction as a function of axial distance in the spray, and you have vapor jet, actual spray model, experimental results, and these are experimental results. Now, this is a transient, so this is actually 0.49 millisecond after start of injection, and this is using a RAND simulation, so it tends to disperse, and so that's essentially why it doesn't capture that head region very well. But if you go further, it does a better job of reproducing the experimental results, and if you go further, it does even better job. But this is within the spray. Radially, we're actually looking at the mixture fraction. Mixture fraction is, in this particular case, you can take it to be the same as the mass fraction of the vapor fuel. Okay? And if you actually look at the distribution, this is probably as good as you can do it. Whether you do it with the spray or the vapor jet, you essentially get the same result. Note that in this particular case, the computed results are all a bit more spread than the actual experimental results, and that's because the K-epsilon model we know. It's using the K-epsilon model for turbulence, which tends to overpredict the spreading a bit. Okay. I have several of these results, but let me skip. You can actually, another problem with this, computing this vaporizing with the spray is that typically what we employ in calculations is a Lagrangian drop Eulerian fluid model. Okay? Now, that model essentially makes certain assumptions. For example, it assumes that the drops are uniformly distributed in a computational cell. Okay, that's an assumption that's made. Now, but at the same time, it says that a computational cell should not have greater than a certain percentage of liquid. Okay, so now there is a bit of a problem, right? Because when you come to the orifice through which you are actually injecting the liquid fuel, you're not able to resolve the liquid fuel, that particular region. So you have to use a grid which is actually larger than the orifice size. Okay, so that's a constraint of these models. Now, this is as good as you can actually get. So this is actually an experimental spray which we were trying to reproduce, and I think it's Jeff Neighbors, one of his sprays from Sandia when he was there. And with the constraints, typically what you can do is you can use a grid size which is about 2 to 2.5 times the orifice diameter in these Lagrangian drop calculations. And so this is actually from Jeff Neighbors' paper, and we are actually comparing computed and measured sprays, penetration in this particular case. Okay. And actually, it's within about 10%, 20% or so. But actually, if you can act, so that disagreement is primarily on account of the fact that you cannot actually numerically resolve the near orifice region. If you can come up with a spray model, which is, if you can actually simulate it in a way where you can actually capture that numerical near orifice region better, then you can get even better agreement with the experimental results. So these circles are actual experimental results, again from the same paper of Neighbor and Siebers. And these are computations using an Eulerian, liquid Eulerian gas two-fluid model, okay, which you can actually use very high resolution. Now, wall interactions are important. Again, we have done some work in trying to reproduce measured wall penetrations. But these simulations are really not very, not completely informative, because it doesn't tell us how much of liquid actually is on the wall in the experiments. So being able to predict, for example, the penetration of this jet along the wall is not necessarily a sign that we are actually doing a good job of capturing all the wall interactions. So a lot of work is probably needed there. And you know, I know that there is a lot of work on individual droplets and trying to relate it to sprays. And this is interesting. For example, here is a case where we looked at it, we took a single droplet in a spray and said, well, if this drop is actually being subjected to this airflow, what does it actually do? And so this is actually, we've done a series of these simulations, but this is from some years ago. But for a Weber number of a certain value on a surrogate number of a certain value, and what you see here is that this drop is highly deformed. And so that contributes to the transfer of momentum, heat, okay, and mass, okay? And typically we, in our Lagrangian drop Eulerian fluid models, we assume it to be spherical, right? I mean, so again, there is a problem. Okay, and of course, collisions, very often what we find is that if you just leave out the effect of collisions, your spray models will do a better job than if you actually use them. Now, I want to summarize this. So with all this, the maximum impact of atomization and spray research in the IC engines area is likely to occur in mid-injection pressure range applicable to low temperature combustion and DISI engine conditions, not in diesel engines or port fuel injection. I think it's good to know, but not very useful in my opinion. Understanding atomization will also provide insight into differences in spray behavior when alternative fuels are employed. I think that's something interesting to do. And so here, for example, is a case where we were trying to compute spray injection into an engine, and we were actually trying to compare this with some experiments that, in fact, the same experiments that I showed earlier by Huang et al. And this is fairly low density, not like a diesel engine. Injection is fairly early during the compression stroke. And so what happens is the spray tends to penetrate a lot more, and there tends to be interaction with the wall. What is shown here is just the vapor fuel, by the way. But the liquid actually interacts with the wall. And so in a situation like this, where we are trying to model this, I think there are a lot of unknowns which it would be good to know. Okay, what is the mechanism of atomization? How does the spray interact with the wall? And that would then help us to improve better engines in this mode of operation. Okay. I had something on biofuels, but it's essentially properties of different fuels, and they can be different, and this can, of course, have an impact on atomization. And I think from the point of view of engines, this is also useful to know. Okay, so recent sponsors of our work, Caterpillar, John Deere, Ford, and Army Research Office. I acknowledge their support. Thank you very much.
Thank you, Professor Abraham. And we can have 2 questions.
Yeah.
Yeah. In the port fuel injectors, although you say the spray studies will not be very much essentials with respect to droplet size, but with respect to spray cone angle or with respect to penetration, because finally most of the sprays actually impinges into the manifold.
Yes.
To know where it is targeting, whether we have, so those kind of studies may be useful, like penetration studies and cone angle for sprays, and also impingement studies with respect to sprays will be possibly useful, if not the droplet size measurement as such. And with respect to the diesel engines, so what you are saying is using a gas jet, particularly high pressure diesel sprays, using a gas jet is sufficient.
Vapor jet, yeah.
Vapor jet is sufficient
Yes.
without bothering about
Yes.
whatever.
Yes.
Okay, thank you.
Yeah.
With respect to the first question, I would like to.
Yes. So with respect to the first question, I have my doubts that there is a whole lot we can gain from what we know today, or we can improve engines from where we are today by focusing on those targeting and all those things. I think that as far as the diesel engine is concerned, the vapor jet, yes. But there is one caveat though. In cold start diesel engines, right, when you're operating cold start, the conditions in the chamber are lower density, lower temperature. So in those engines, it is possible that, in fact, it is likely that the liquid will penetrate much longer than this. Okay, so I mean, I said all those things, but we have to keep that caveat in mind. Yes.
Very interesting talk. I do agree with you partially that in terms of IC engines, probably we've milked that thing dry, atomization. But the caveat that you pointed out is interesting, I think, that in the diesel one you showed where the gas jet is equivalent, it's possibly very close to critical. There's probably not even an interface at the liquid vapor in the droplets. Is that true?
Okay, well, so this is an interesting question, right? So there was a paper that came out at the ILAS meeting in Ventura. Were you there?
No.
No, at Ventura by Joe Orfelein's group from Sandia. I think Rainer Dahms or somebody was the co-author, where they suggested that the spray in the diesel engine really doesn't exist as a liquid. It's just because it's supercritical. I'm not so sure. In fact, I disagree with that. It's true that the temperature is almost always supercritical. The pressure would be maybe supercritical too. But that doesn't mean that the entire liquid is supercritical, right? Because it is vaporizing. So when you vaporize, it cools, and so the actual when you inject the liquid, the temperature is in fact lower than the critical. And some droplet vaporization studies we've done some years ago show that actually that droplet temperature never really reaches the critical unless the critical temperature is, unless the actual temperature is twice the critical value, okay, or the pressure is twice the critical pressure.
Yeah,
I mean,
I don't disagree with that, but
he probably has done something similar too at UI. Yes, yes.
But I guess where I was coming from was that the momentum transfer, if you have an interface, would presumably be different than if you didn't have a well-defined interface.
Yes.
So I was rationalizing your
yes.
good match of the gas jet
Yes.
based on
That's the possibility. Yes, but the point is that if you use, so you could get the same thing if your drop sizes are extremely small, right?
Just as a quick, if you don't mind, quick point. This half an hour that we set aside is for discussion on all the 3 lectures. So please feel free to ask questions. Please feel free to bring up any of the issues that were mentioned in the earlier lectures as well.
Yes.
Regarding the drop deformation in gas flow that you have shown the result, is it an evaporating drop in a high temperature gas flow that you have shown?
Oh, the one which I just showed about the deformation?
Right.
No, it is not in that particular one.
Understand how much it will influence that Lagrangian droplet cracking thing which you were talking about. If it is, what is the time scale, order of time scale? In case of an evaporating drop,
Yes.
if you consider the droplet life.
Oh, I see what you're saying. So what you're saying is that maybe before it actually deforms, it's actually evaporated, right? That is a possibility if it's a very small drop, because the drop vaporization characteristic time would be certainly less than a millisecond, right? And so that deformation time is of the same order. And so you're absolutely right.
In that case, probably that Lagrangian.
It probably doesn't matter. The transfer is going to be fast anyway, right? It's going to become vapor.
Okay, just a quick comment. So, Professor Abraham, earlier you were talking about this supercritical injection. I think the work you're talking about from Joe Flynn's group, they used N-heptane. So that's why it's easier to ensure that it's actually supercritical. But if you're actually doing a diesel injection, it's difficult to see that it's supercritical. So just a quick comment.
Yeah, that's possible. Yeah. I mean, it was a computational study,
Exactly.
but they were using N-heptane
As a surrogate
properties,
well, so.
right? And they don't really have the property. So I had a long discussion with Joe. They don't really have the property, some of those properties well.
Right, I had a similar discussion too.
Yeah. Yes.
One is in the experiment that you showed us, what is the uncertainty in measurement for the mean mixture fraction?
Yes, so that so there is that uncertainty in the paper we have actually reported that.
Okay.
Yeah.
And second comment was you just referred in the last slide that coalescence is not so important. Kind of surprising that the gas turbine community always believed that was not important, but the diesel community always believed it was important. And you seem to say that you discovered or you found that it's not important. It's interesting.
Well, okay. It may or may not be important, but when we do computational modeling, trying to capture that is a big challenge. Okay, especially with the kind of models we employ for engine simulations.
Okay, but I thought a lot of the models that were developed for coalescence were actually developed based on all the measurements that diesel.
No, I don't think so. I think it was it is based on observed behavior, maybe in raindrops and so on and so forth, right? Far removed from.
We have seen a lot of isolated drop impact experiments in support of many of these models. Even in your own work, the isolated drop coalescence, how the results or the experimental outcomes, how important they are for the real model, or how good they are for the real jet model or spray model?
Isolated drop studies.
You know, we have isolated drop impact on solid surfaces. Many work, we can see it in connection with the spray impact.
Right. So I think to an extent they are useful. But I don't think we should equate individual isolated drop impact studies with spray impact. They are different, right? Because so when you have a spray impact, I mean, you could get a surface that's completely covered with a liquid film, and then you have these drops which are then impacting on that. And you know, there's a transient effect with the buildup of a film. So it can be quite different, right? But so I think to an extent they are useful though.
Because there are many literature they directly take.
I know, but I'm always concerned about that. I mean, in other words, taking isolated drop wall impact studies and trying to develop models from just that and employing it directly in spray models.
Yeah.
It's a bit.
The question is about the behavior of diesel engine sprays. What's your opinion on comparison of biodiesel sprays and diesel sprays?
In terms of, is it, what is the,
let's say the in-cylinder
can you
spray.
make that question a bit more precise? In other words, are biodiesel sprays likely to show differences from diesel sprays?
Exactly, yes.
Yes. Now, the extent to which, so we have a liquid length which is 1 centimeter, right? I said. If in the case of a biodiesel spray, it is 1.1 centimeter, is it important? I don't know. Now, if it is 1.5 centimeter, yeah, maybe it. You see what I'm saying? So it depends. But that's something that needs a bit more study and exploration. Yes.
So you are talking about stratified charge engines, and mixing is very important there. So what is your suggestion on a figure of merit parameter for stratification in a DISI kind of engine?
Yes, I think that's, I mean, so to come up with that, so we've come, I have seen different proposals for doing that, and we have proposed something on our own. I think that's important, yes. If you can come up with a good figure of merit parameter.
Okay, thank you.
I have a question for Professor Raghunandan. First,
I think I don't need to stand here because maybe. Yeah, no. Okay.
Yeah.
Well, actually, there are several people. Maybe everybody should come up or something. I don't know.
This is regarding the jet and cross flow work that you presented in the last part of your lecture. I was interested in knowing, what's the range of pressures that you were looking at?
This pressure, I think I will. Surya Prakash, will you tell what pressures you work with for the jets? This is the airstream. This is the
the airstream.
airstream.
The airstream.
Is in atmospheric pressure.
And
okay, the jet is perhaps.
Okay. I was interested in the airstream.
No, airflow is.
Okay. And what about? Was there any pressure gradient imposed in the airstream?
No.
Did you actually impose any?
No.
Is there a plan to do any of those in future?
Well, we should do, but I think I want to see. First of all, this is like a small tunnel we have constructed. Looking at it from there, but then we can create gradient. We did actually long ago on combustion. We had done the gradient close to this, but this is a little.
Are you following the work that's being done in Georgia and other universities on jet infrastructure?
Sure, I'm referring to the literature.
Okay. All right. Thank you.
We'll have more opportunity to come back for more discussion, but probably have about 5 minutes for before lunch is set up. If you have any more questions, we can take them.
Question to Achintya. Well, all the studies on various studies that you mentioned, how well do they compare with the results from this data when used to compare performance prediction, at least in the sector, how well do they?
Actually, I have not seen using this impact of these models on actual combustor systems. This has been more like fundamental kind of studies.
We have a couple of publications. I think if you refer to Hukum Mungia's papers that have been published in 2007, 8 or earlier, 2003, 4, we've done the air blast simplex. In fact, CFM56, one of the air blast nozzles that we use commercially has been extensively studied. There is some experimental versus computational comparisons that have been done for that.
There are some works by SOM in the IIT KGP, and also the Ganeshan. They had done some work on gas turbine, and it is matching fairly well with their respective experimental data taken from various. What I had reviewed some papers a long time back, and I could see there is a reasonably well comparison with that.
In fact, the model that we use for linear stability analysis is from Jayanshekhar and Milinjo. So. But it's a two-step process. There's a description of that given in one of the papers. Probably.
Okay, I think I'll move away from this. Maybe this is a good point to pause. We've had a sort of a very good seed 3 presentations to start off on for the afternoon. We have a series of presentations on secondary atomization, multi-phase flow, and internal nozzle issues following that. So we'll break for lunch now.